What if I told you that for hundreds of millions of years, our universe existed in total darkness, no stars, no galaxies, just an endless sea of shadow stretching across the cosmos? This wasn't some fleeting moment after the Big Bang. It was an entire era, a cosmic dark age so profound it makes the medieval period look like a brief power outage. Picture this, a newborn universe still cooling from its fiery birth, filled only with a fog of hydrogen gas so thick not a single beam of light could pierce it. For over 380,000 years after creation, space was a silent, lightless expanse waiting for something, anything, to ignite the darkness. And then nothing happened, at least not for ages. This eerie, quiet period lasted until the first stars finally flickered to life, ending the cosmic night. But what exactly happened during those mysterious years? How did the universe go from a blank, featureless void to the glittering tapestry of galaxies we see today? Scientists call it the Dark Ages of the universe, and it's one of the greatest unsolved puzzles in all of astrophysics. We're talking about a time before stars, before planets, before even the faintest glow of cosmic dawn. A time so ancient we can't observe it directly, only theorize, speculate, and piece together clues hidden in the faintest whispers of radiation left behind. That's where things get truly fascinating, because while we can't see this era, we've come up with some astonishing theories to explain it. Some suggest the universe wasn't completely dark, just hiding invisible forces or exotic particles we've yet to discover. Others propose that the first black holes may have formed in this void, silently shaping the cosmos before light ever returned. And then there's the wildest idea of all. What if the Dark Ages weren't empty at all, but teeming with forms of energy or matter so strange, so alien, that we haven't even imagined them yet? Over the next 30 theories, we'll dive deep into these possibilities, uncovering the boldest, most mind-bending ideas scientists have proposed to solve this cosmic cold case. So buckle up, we're about to explore an era of the universe so mysterious, it makes black holes look straightforward. To uncover the secrets of the Dark Ages, scientists turn to the oldest photograph in existence, the cosmic microwave background, or CMB. This faint glow is the universe's very first light, emitted when the cosmos was just 380,000 years old. Think of it like a cosmic fingerprint, preserving the exact conditions of the infant universe in its ripples and shadows. But here's what's truly remarkable: those subtle variations in temperature and density, almost imperceptible to the naked eye, hold the blueprint for everything that came after. Those tiny fluctuations, no larger than 1 part in 100,000, were the seeds of destiny. Dense regions pulled in more hydrogen gas, slowly growing heavier under their own gravity, while emptier patches stretched thinner. Over millions of years, that imbalance set the stage for the first stars and galaxies to form. It's like tracing the roots of a mighty oak tree back to a single, fragile seed. The CMB shows us where the cosmic construction sites were, regions where matter began clumping together long before the first spark of starlight. And yet, despite this incredible snapshot, the Dark Ages themselves remain frustratingly invisible. The CMB gives us the before picture, but the period that followed is like a missing chapter in a cosmic novel. For hundreds of millions of years, the universe expanded, cooled, and quietly prepared for its next act, all while shrouded in perfect darkness. The only way we can piece together what happened is by studying the echoes left behind, like an astronomer reconstructing a storm from the ripples it left in a pond. This is where theory and imagination collide. Some researchers suggest that dark matter, the invisible scaffolding of the cosmos, may have started gathering into halos during this era, long before ordinary matter caught up. Others speculate that mysterious energy fields or even primordial black holes could have lurked in the shadows, subtly bending space and time without emitting a single photon. The CMB hints at these possibilities but keeps its secrets close, leaving us to wonder what other forces might have been at work in that endless night. One thing is certain: without those delicate density variations imprinted in the CMB, our universe would look drastically different. No galaxies, no stars, just a vast, empty void. So while we can't directly observe the Dark Ages, we know they were anything but uneventful. Hidden in that darkness, the fate of the cosmos was being written. One of the most radical theories about the Dark Ages suggests the darkness wasn't empty at all, but crawling with black holes. Not the massive, star-devouring monsters we know today, but strange, ancient relics from the very birth of the universe. Imagine trillions of tiny black holes, each no heavier than an asteroid, scattered like invisible seeds across the cosmos. These so-called primordial black holes could have formed in the first chaotic seconds after the Big Bang, when density fluctuations were so extreme that pockets of space-time collapsed under their own weight. And if they existed, they might have been the universe's dominant form of matter long before stars ever lit up the sky. What makes this idea so compelling is how neatly it solves several cosmic mysteries at once. Ordinary matter, the hydrogen gas filling the early universe, would have taken hundreds of millions of years to clump together under gravity alone, but primordial black holes, their gravity incarnate, even a speck-sized black hole would have exerted an outsized pull on its surroundings, acting like a cosmic anchor for gas to gather around. Some researchers argue these black holes could have jump-started the formation of the first stars and galaxies, serving as hidden scaffolding for the universe's grand design. There's even a tantalizing link to dark matter. We still don't know what makes up this invisible substance that outweighs normal matter 5-to-1. But if a fraction of those primordial black holes survived to the present day, they could account for at least some of that missing mass. Picture this: an unseen ocean of ancient black holes lurking between galaxies, their collective gravity bending light and warping space in ways we're only beginning to detect. Of course, not everyone's convinced. Critics point out that if these black holes were everywhere, we'd expect to see more evidence, like bursts of radiation from their eventual evaporation or distortions in the cosmic microwave background. Yet the absence of proof isn't proof of absence. The Dark Ages were, by definition, an era of obscurity, and if there's one thing black holes excel at, it's staying hidden. The wildest twist: some models suggest these primordial black holes might not even be black in the traditional sense. Quantum effects could have given them bizarre properties, like leaking energy or even merging into larger structures over time. It's a reminder that in the darkness of the early universe, the rules as we know them might not apply, and what we call impossible could just be waiting for the right discovery. While black holes may have lurked in the darkness, there's another invisible force that likely dominated the cosmic stage during the Dark Ages: dark matter. This mysterious substance, which makes up roughly 85% of the universe's mass, doesn't interact with light or ordinary matter in any way we can detect. Yet its gravitational pull is so immense, it's thought to have sculpted the universe's very structure. Imagine dark matter as the unseen architect of the cosmos, silently weaving a vast web of gravitational potential long before the first stars switched on. Here's how it might have worked. In the early universe, dark matter's gravity began pulling matter into dense knots and filaments, creating an intricate cosmic skeleton. Ordinary hydrogen gas, the stuff that would eventually form stars, simply flowed along these invisible pathways, pooling in the deepest gravitational wells. Think of it like water following the contours of a landscape it can't see. Without dark matter's hidden scaffolding, gas would have spread too thinly, delaying star formation by billions of years. Some simulations suggest dark matter did more than just provide structure. It may have accelerated the birth of the first stars. Small clumps of dark matter, called halos, could have acted as gravitational traps, concentrating hydrogen gas until it grew hot and dense enough to ignite nuclear fusion. These protostars might have been unlike anything we see today, monstrously large, blazing briefly before exploding in violent supernova that seeded the cosmos with heavier elements. But here's the twist: dark matter's influence wasn't uniform. In regions where it clustered tightly, stars may have formed earlier and more vigorously. In emptier areas, the dark ages could have dragged on longer, leaving patches of the universe in extended twilight. This uneven timeline might explain why some galaxies appear older than others, as if the cosmos flickered to life piece by piece. The wildest part, we still don't know what dark matter actually is. Is it a particle, a wave, something beyond our current physics? Whatever its nature, one thing's clear: the universe's transition from darkness to light wasn't just a story of gas and gravity. It was a dance choreographed by an invisible partner whose steps we're only beginning to trace. The mystery of the missing baryons is one of the most perplexing puzzles of the cosmic dark ages. Baryons, the ordinary matter that makes up stars, planets, and even us, should account for roughly 4% of the universe's total mass. Yet when astronomers tally up all the visible matter in galaxies and clusters today, they come up startlingly short. Nearly half of the baryons predicted by the Big Bang seem to have vanished without a trace. So where did they go? The answer might lie in the darkness itself. During the Dark Ages, baryons weren't missing, they were just hiding in plain sight. Instead of clumping into dense, glowing stars, most of the universe's ordinary matter likely existed as an ultra-thin fog of hydrogen gas, spread so diffusely across space that it emitted almost no detectable light. Picture a vast, invisible ocean filling the gaps between galaxies, too sparse to shine but too pervasive to ignore. This intergalactic medium, known as the warm-hot intergalactic medium or WIM, could be the secret reservoir of those elusive baryons. It's like searching for water in a desert and realizing it's been suspended as humidity in the air all along. But there's another twist. Some theorists suggest these baryons might have taken on even stranger forms. In the extreme conditions of the early universe, ordinary matter could have been locked into exotic states like quark-gluon plasma, a primordial soup where protons and neutrons hadn't yet formed. Or perhaps baryons were trapped in dense, dark filaments of gas, strung like invisible threads between the first gravitational wells. These structures, far too faint for current telescopes to spot, would have silently shaped the cosmos while remaining hidden from view. The hunt for these missing baryons has led scientists to ingenious methods. By studying how light from distant quasars filters through space, researchers have detected faint traces of ionized oxygen and other elements, hints that the WIM is real and far more extensive than we once thought. Other clues come from the cosmic microwave background, where subtle distortions in its afterglow might reveal how baryons were distributed during the Dark Ages. It's a bit like reconstructing a crime scene from fingerprints no one knew were there. Yet the story doesn't end there. Some models propose that a fraction of baryons could have been ejected from galaxies entirely, flung into the void by violent supernova explosions or the fierce winds of early quasars. These rogue atoms, stripped of their electrons and racing through intergalactic space at millions of kilometers per hour, would be nearly impossible to track. They're the cosmic equivalent of footprints washed away by the tide. The missing baryon problem reminds us just how much of the universe remains unseen. Even ordinary matter, the stuff we're made of, can slip through the cracks of our observations. But with every new telescope and simulation, we're peeling back the layers of that ancient darkness and inching closer to solving one of cosmology's greatest disappearing acts. Hidden in the silence of the Dark Ages may be a whisper, a faint radio signal from the very hydrogen that blanketed the early universe. This isn't just any static. It's a specific wavelength, 21 centimeters long, emitted when the spin of a hydrogen atom's electron flips. And if we could detect it, this signal would act like a cosmic sonar, revealing the structure of the universe during its most mysterious era. Imagine tuning a radio to a frequency no one's heard for over 13 billion years and suddenly hearing the universe's oldest song. This 21-centimeter signal is the closest thing we have to a time machine. Neutral hydrogen gas, which filled the cosmos during the Dark Ages, absorbed and re-emitted energy at this exact wavelength as it interacted with the faint light of the cosmic microwave background. The slight variations in this signal, warmer here, cooler there, would map the density of the early universe in unprecedented detail. It's like finding a fossilized ripple in a pond, preserving the exact shape of the stone that caused it long after the splash has faded. But catching this signal is one of the hardest challenges in modern astronomy. The waves have been stretched by the expansion of the universe, shifting them from 21 centimeters to over 2 meters by the time they reach us. Worse, they're drowned out by a cacophony of modern radio interference, everything from cell phones to satellites. It's like trying to hear a pin drop in a thunderstorm. Despite the obstacles, teams like the Hydrogen Epoch of Reionization Array and the Square Kilometer Array are racing to capture this elusive signal. Their strategy: build antennas in some of the most remote places on Earth, radio-quiet deserts and high plateaus, and use supercomputers to filter out the noise. If they succeed, the payoff would be staggering. We could see the first cosmic structures forming in real time, watching as dark matter's gravitational pull sculpted hydrogen into the seeds of galaxies. There's even a wilder possibility. Some theorists suggest the 21-centimeter signal might carry imprints of phenomena we've never detected, like primordial magnetic fields or interactions with dark matter particles. If so, this faint radio hum could be the key to unlocking not just the Dark Ages, but the very nature of reality itself. The universe left us a voicemail. Now we just have to find a way to play it. One of the deepest mysteries of the Dark Ages isn't just the darkness itself, but why it lasted so incredibly long. Picture a universe primed with hydrogen, gravity doing its work, yet no stars sparking to life for hundreds of millions of years. It's like waiting for a campfire to ignite when all the wood is soaked in gasoline. So what cosmic traffic jam kept the lights off for so long? The answer might lie in the universe's awkward teenage phase, a time when nothing worked quite right. For stars to form, hydrogen gas needs to cool down enough to collapse under its own gravity. But in the early universe, cooling was anything but efficient. Without heavy elements like carbon or oxygen, which wouldn't exist until the first stars exploded, the only way for gas to shed heat was through molecular hydrogen, a fragile molecule easily torn apart by stray radiation. This created a cosmic catch-22. Gas couldn't collapse until it cooled, but it couldn't cool effectively without already being dense. Simulations show these first star-forming regions may have fizzled and restarted countless times before finally reaching critical mass. Then there's dark matter's controversial role. Some models suggest certain types of dark matter particles could have interacted with hydrogen, subtly heating the gas and delaying collapse. Imagine trying to freeze a lake while invisible hands keep stirring the water. Other theories propose dark matter wasn't just a spectator. It may have formed dark stars first, gigantic objects powered by dark matter annihilation rather than nuclear fusion. These bizarre structures could have hogged hydrogen for eons before finally giving way to normal stars. The wild card, turbulence. The early universe wasn't a serene pool of gas. It was a churning, violent place where shockwaves from the Big Bang's aftermath sloshed matter around like water in a shaken bottle. This chaos may have prevented gas from settling into the calm, dense pockets needed for ignition. Add to that the relentless stretching of space itself, constantly diluting matter and working against gravity's pull, and you've got a universe fighting its own birth. Perhaps the most humbling possibility is that there was no single bottleneck, just a perfect storm of minor obstacles. Like a Rube Goldberg machine with 100 delicate steps, the path to the first starlight required everything to align just so. When we look up at the night sky today, we're seeing the survivors of that cosmic trial by fire, the stars that finally beat the odds and ended the universe's longest night. We often think of the early universe as a place ruled solely by gravity, a vast, chaotic dance of matter pulled into clumps by nothing more than its own weight. But what if another invisible force was also at work, subtly shaping the cosmos in ways we're only beginning to uncover? Enter magnetic fields, the unsung architects of the Dark Ages. While today's galaxies are threaded with powerful magnetic forces, their origins have long been a mystery. Some scientists now believe these fields didn't emerge with the first stars. They were there from the beginning, woven into the fabric of space itself, quietly directing the flow of gas like cosmic rivers carving their path. The idea starts with a faint whisper of magnetism in the infant universe, possibly generated by quantum fluctuations in the seething plasma of the Big Bang. These primordial fields would have been unimaginably weak, billions of times fainter than Earth's magnetic field, but over millions of years, the colossal motions of collapsing gas and dark matter could have amplified them. Picture a slow-motion dynamo. As hydrogen swirled into the first galactic disks, these feeble magnetic lines might have stretched, twisted, and intensified, eventually growing strong enough to influence where gas pooled and stars ignited. Here's where things get fascinating. Simulations show that even a weak magnetic field could have acted like a cosmic traffic cop, preventing gas from collapsing haphazardly and instead channeling it into dense, spinning filaments. Without this guidance, early star-forming regions might have remained bloated and inefficient, like fires struggling to catch in a stiff wind. But with magnetism's subtle nudge, gas could have funneled into tighter spirals, reaching the critical densities needed to spark the universe's first true stellar nurseries. The implications are staggering. If magnetic fields played a role in the Dark Ages, they might explain why some galaxies formed earlier and more efficiently than others. Regions where these primordial fields were slightly stronger could have become hotspots of star birth, while weaker areas lagged behind. It's like discovering that the blueprint for today's glittering cosmic cities was drawn not just by gravity's hand, but by an invisible ink of magnetism we've only just learned to see. Yet proving this theory is a monumental challenge. Primordial magnetic fields would have left only the faintest fingerprints, perhaps subtle distortions in the polarization of the cosmic microwave background, or telltale twists in the way distant galaxies align. New telescopes like the upcoming Square Kilometre Array are hunting for these clues with unprecedented precision. If they succeed, we might finally solve one of the Dark Ages' quietest mysteries: how the universe learned to write its story in invisible lines of force. And there's an even wilder possibility. Some theorists speculate these ancient fields could be relics of phenomena far stranger than the Big Bang cosmic strings, phase transitions in the early universe, or even echoes of a pre-Big Bang era. Whatever their source, one thing is clear: magnetism's whisper may have been the universe's first language, spoken in the dark long before the stars began to shine. At the smallest scales imaginable, far smaller than an atom, smaller even than the particles within it, the early universe was a seething ocean of quantum uncertainty. Empty space wasn't truly empty, but a bubbling cauldron where particles and energy flickered in and out of existence in fractions of a second. These quantum fluctuations, random blips in the fabric of reality, might seem insignificant. Yet they hold the key to one of the greatest cosmic mysteries: how a universe that began in perfect uniformity grew into the intricate web of galaxies and voids we see today. The magic lies in inflation, the universe's explosive growth spurt in the first sliver of a second after the Big Bang. As space expanded faster than light itself, those microscopic quantum ripples were stretched to astronomical sizes, frozen into the very structure of the cosmos. Imagine blowing up a balloon with tiny dots on its surface. As it inflates, the dots grow into continents. Similarly, what began as subatomic wrinkles became the seeds for all cosmic structure, slightly denser regions where extra matter gathered and thinner zones where less existed. Without these imperfections, gravity would have had nothing to grip, no starting points to build galaxies, stars, or planets. The universe would have remained a featureless soup forever. Here's where it gets truly mind-bending. The patterns we see in today's universe, the sprawling filaments of galaxies, the vast empty voids between them, are essentially quantum mechanics written on a cosmic scale. The cosmic microwave background, that ancient afterglow from the infant universe, shows temperature variations that match predictions of quantum theory with eerie precision. It's as if the universe took the ghostly whispers of uncertainty that govern the subatomic world and amplified them into the architecture of existence itself. But quantum fluctuations didn't just set the stage, they may have dictated the universe's ultimate fate. Some regions, by random chance, started with a tiny extra density, allowing them to collapse into galaxies earlier. Others, slightly emptier, evolved into the desolate voids that dominate cosmic geography. This cosmic lottery, drawn in the first trillionth of a second, determined where life could eventually arise billions of years later. The Milky Way, Earth, even your existence traces back to those fleeting quantum ripples, and the implications go deeper still. Certain theories suggest these fluctuations weren't entirely random, but carried faint imprints of even earlier physics, perhaps echoes of a pre-Big Bang universe or evidence of hidden dimensions. If so, the quantum blueprints of the cosmos might be our only window into realms beyond space and time. The Dark Ages weren't just a pause between cosmic events, they were the unfolding of a story written in the smallest handwriting imaginable, now stretched across the sky for us to decipher. Before stars could ignite, the universe needed to cool down, and that required the first chemistry experiment in cosmic history. Picture a scorching young cosmos filled with ionized hydrogen, gas so hot that atoms couldn't hold onto their electrons. In this plasma furnace, no molecule could survive until temperatures finally dropped enough for something extraordinary to happen. The universe's first molecular handshake, a fragile bond between a hydrogen atom and a helium ion, forming hydrogen-helium hydride or He+. This simple molecule, just 3 particles clinging together, was a game changer. Why? Because molecules, unlike lone atoms, can radiate heat away efficiently through rotation and vibration. Imagine the difference between trying to cool a red-hot piece of metal by waving it in the air versus plunging it into water. He+ acted like that water, allowing dense pockets of gas to shed energy faster than ever before. Without this molecular coolant, hydrogen might have remained too energetic to collapse under gravity, prolonging the Dark Ages indefinitely. Here's how it worked. As the first He+ molecules formed, they began emitting infrared light, carrying away thermal energy like cosmic radiators. This cooling effect caused gas clouds to contract, creating denser regions where gravity could gain the upper hand. Over time, these chilled, shrinking pockets became the nurseries for the very first stars. It's a bit like how mist condenses into droplets on a cold window, except on a scale spanning light years. But there's a twist. These pioneering molecules didn't last long. The intense ultraviolet light from the first stars would have quickly torn them apart, recycling their components into new molecular combinations. In a way, He+ was both midwife and martyr, ushering in the era of starlight only to be destroyed by it. What's astonishing is how delicately balanced this process was. If molecular cooling had been slightly less efficient, star formation might have stalled. Too efficient, and gas could have collapsed into countless tiny, faint stars instead of the massive behemoths we think dominated the early cosmos. The universe's recipe for starlight required just the right pinch of molecular magic, a golden ratio written in the bonds of the simplest molecules imaginable. And this isn't just theory. In 2019, astronomers detected H+ for the first time in a planetary nebula, a relic of stellar chemistry that hints at how these molecules once shaped the cosmos. It's like finding an ancient tool that helped build civilization, still lying in the ruins of a modern city. The Dark Ages may have been dark, but they were far from simple. Every flicker of starlight we see today owes a debt to these primordial molecules that first taught the universe how to cool its heels. Dark energy is the universe's greatest mystery today, an invisible force pushing galaxies apart at ever-increasing speeds. But what if its influence didn't begin with the modern era of cosmic acceleration? What if this phantom energy was subtly at work even during the Dark Ages, shaping the universe's evolution in ways we've barely begun to imagine? Most theories assume dark energy only became significant billions of years later, when the universe was already middle-aged. Yet some researchers are now questioning that timeline, daring to ask, could dark energy have left fingerprints on the cosmos long before its dramatic takeover? The math tells a tantalizing story. If dark energy's strength has changed over time, a theory known as quintessence, it might have been far weaker in the early universe, but not entirely absent. Even a whisper of repulsive gravity could have altered how quickly matter clumped together in those critical first eons. Picture a vast cosmic tug-of-war, dark matter's gravity pulling gas inward, while a faint push from dark energy resisted just enough to slow the process. The result, a delicate balancing act where the first stars flickered to life slightly later, or in different configurations than they would have otherwise. It's like realizing a gentle breeze you barely noticed at sunrise was quietly steering the course of a drifting ship all along. Here's where observations get intriguing. The cosmic microwave background shows slightly less matter clustering than some models predict, especially on the largest scales. Could this be a relic of early dark energy gently suppressing structure formation? Some simulations suggest yes, that even a fraction of dark energy's current strength during the Dark Ages would leave detectable gaps in the universe's large-scale web. These voids and filaments might be cosmic fossils, preserving the moment when phantom energy first flexed its invisible fingers. But the wildest possibility isn't just about strength, it's about behavior. If dark energy interacted with dark matter or even ordinary atoms in those early epochs, it could have triggered exotic effects we'd never see today. Imagine regions where dark energy briefly switched off, allowing matter to collapse explosively into supermassive black holes, or pockets where it fluctuated unpredictably, creating bizarre bubbles of accelerated or slowed time. The Dark Ages might have been a laboratory for physics we can no longer observe, a playground for forces that faded as the universe grew older. Of course, not all clues point the same way. Critics argue that if dark energy were active so early, we'd see clearer distortions in the cosmic microwave background or galaxy distributions. Yet absence of evidence isn't evidence of absence, especially when dealing with an energy that, by definition, hides in plain sight. The truth might lie in subtle anomalies, like slight variations in the timing of reionization or unexpected patterns in the oldest quasars. Like detectives piecing together a crime from decades-old crumbs, astronomers are sifting through ancient light for hints of dark energy's shadowy debut. One thing is certain, if dark energy did leave its mark on the Dark Ages, it would rewrite our understanding of cosmic history. No longer just a latecomer to the universe's expansion, it would be a player from the very beginning, a silent director guiding the show long before the stars took center stage. And that raises an even deeper question. If dark energy's influence has evolved, what else might it do in the future? The Dark Ages could hold the key not just to our past, but to the universe's ultimate fate. The first starlight should have been a beacon, a signal that the universe's long night was finally ending. But what if those early stars weren't just lighting up the cosmos, but inadvertently keeping it dark? This paradox lies at the heart of the Lyman-Werner bottleneck, a cosmic catch-22 where the very photons meant to herald a new era became prison bars for progress. Here's how it worked. When the earliest stars ignited, they blazed with intense ultraviolet radiation, specifically photons at wavelengths known as Lyman-Werner bands. These energetic particles didn't just travel freely through space, they slammed into surrounding hydrogen gas, not merely bouncing off but performing an atomic-scale magic trick. Upon absorption, they'd temporarily excite hydrogen molecules, only for those molecules to later re-emit the energy as infrared light and return to their original state. The result, a near-perfect trap where ultraviolet starlight got converted into harmless heat instead of breaking molecular bonds. This created a chilling side effect. For new stars to form, hydrogen gas needed to cool and collapse under gravity. But cooling required molecular hydrogen, delicate pairs of atoms that could radiate heat away through rotation and vibration. The trouble was, those same Lyman-Werner photons that couldn't escape the gas were also just energetic enough to rip hydrogen molecules apart when they did occasionally interact. Picture trying to fill a leaky bucket. The harder you pour, the more stars ignite. The faster the leak's molecular destruction cancel out your progress. Astoundingly, this bottleneck may have throttled star formation for millions of years. Regions where the first stars burned brightest could have sterilized their surroundings, suppressing further stellar births until enough hydrogen recombined, a self-regulating cycle where cosmic dawn advanced in fits and starts. Some simulations suggest entire mini-eras of starburst and quiescence might have pulsed through the early universe, like a fluorescent light flickering before it stabilizes. The implications are profound. Without this bottleneck, stars might have formed too rapidly, exhausting the universe's fuel before galaxies could take shape. Instead, the Lyman-Werner effect acted as a cosmic metronome, pacing the transition from darkness to light in a way that allowed complexity to emerge. It's a reminder that even the simplest physical processes, photons interacting with atoms, could hold the keys to the universe's grand narrative, and somewhere out there, the faint echoes of those trapped photons may still linger, whispering the story of how the cosmos learned to regulate its own awakening. Among the most intriguing candidates for dark matter's identity is a ghostly particle called the action, a hypothetical speck of matter so light it could pass through a planet like sunlight through glass. Unlike bulky WIMP or primordial black holes, actions would have moved through the early universe like a silent wind, barely interacting with ordinary matter, yet potentially shaping the dark ages in ways no other particle could. Picture a cosmic ballet where gravity isn't the only choreographer, where invisible particles pirouette through space, subtly slowing or speeding up the birth of the first stars. The action's origin story begins with a puzzle in particle physics. In the 1970s, scientists realized the strong nuclear force which glues atomic nuclei together mysteriously respects a near-perfect symmetry that, by all rights, it should break. To explain this, theorists proposed the action as a sort of cosmic peacekeeper, a particle whose existence would preserve this symmetry. But here's the twist: if actions exist, they'd also behave exactly like cold, dark matter, clumping around galaxies just as observations demand. It's as if the universe repurposed a solution to one physics riddle to solve another. What makes actions especially fascinating for the Dark Ages is their uncanny ability to transform. In strong magnetic fields, these particles can briefly morph into photons, flashes of light where none should exist. During the cosmic night, this conversion could have created faint, sporadic glows in hydrogen clouds like fireflies flickering in a fog. Even more remarkably, actions may have acted as cosmic refrigerators. As they oscillate between states, they emit minuscule amounts of energy, cooling surrounding gas ever so slightly. In a universe where star formation hinged on delicate temperature balances, This cooling could have nudged dense regions toward collapse earlier, or delayed them depending on the action's exact mass. Simulations reveal how dramatic these effects might have been. If actions are as light as some models suggest, their quantum waves could have stretched across entire proto-galaxies, smoothing out density fluctuations like a gentle cosmic iron. Heavier actions, by contrast, would have behaved more like a fine mist, collecting in gravitational wells and accelerating star formation locally. The difference: a universe where galaxies ignite uniformly versus one that flickers to life in scattered, brilliant sparks. The hunt for these elusive particles is pushing technology to its limits. Experiments like ADMS use powerful magnets and ultra-sensitive detectors to listen for actions converting into radio waves, a process likened to tuning a cosmic radio to a station that might not exist. Others search for action imprints in the cosmic microwave background's polarization patterns, where their ghostly interactions could have left faint swirls in the ancient light. But the boldest clue might come from the Dark Ages themselves. If actions altered the timeline of reionization, the epoch when starlight finally flooded the universe, their signature could linger in the spectrum of the earliest galaxies. It's a tantalizing possibility that the solution to one of particle physics' greatest riddles has been hiding not in some high-energy collider, but in the silent echoes of the universe's longest night. What's striking is how such a lightweight particle could leave heavyweight fingerprints. The action reminds us that in the darkness before stars, the tiniest forces might have written the rules for everything that followed. And if we're right about their role, we're not just uncovering dark matter's identity, we're decoding the hidden instructions for how the cosmos learned to shine. For decades, cold dark matter has been the leading explanation for the invisible scaffolding of our universe, slow-moving, massive particles that clumped together early on, forming gravitational wells where galaxies could grow. But there's a problem. Simulations based on this theory predict a universe teeming with countless dwarf galaxies, tiny satellites orbiting larger ones like fireflies around a lantern. Yet when we look at the actual cosmos, these small galaxies are suspiciously scarce. It's as if someone took a cosmic eraser and wiped away half the expected structures. This glaring mismatch has led some scientists to consider a radical alternative. What if dark matter isn't cold at all, but warm? Warm dark matter proposes a subtle but game-changing twist. Instead of sluggish, heavy particles, imagine dark matter made up of lighter, faster-moving specks, zipping through space like a swarm of energetic neutrinos. This slight shift in properties could solve the missing dwarf galaxy puzzle neatly. Here's why. Cold dark matter's sluggishness allows it to clump easily, even on very small scales, creating countless tiny gravitational traps where dwarf galaxies should form. Warm dark matter, by contrast, moves too quickly to settle into such fine-grained structures. Its particles would smear out density fluctuations below a certain size, like waves smoothing over sandcastles on a beach. The result, far fewer tiny galaxies matching what we actually observe. The implications ripple outward. If warm dark matter is real, the first structures in the universe wouldn't have been countless microscopic clumps, but a sparse network of medium-sized filaments, cosmic arteries where gas could collect and eventually ignite the first stars. This might explain another oddity. Some of the earliest galaxies we've spotted with telescopes like JWST appear surprisingly massive and mature for their age. Warm dark matter's preference for larger-scale structures could have allowed these giants to assemble earlier than cold dark matter would permit. Yet the theory isn't without its critics. Skeptics point out that warm dark matter struggles to explain other observed features, like the intricate substructure within galaxy clusters. There's also the question of what particle could even fit the bill. The prime candidate, sterile neutrinos, remains hypothetical, though experiments are hunting for them in nuclear decays and cosmic rays. And some researchers argue that alternative solutions, like cosmic rays or supernova winds blowing gas out of small galaxies, could account for the dwarf deficit without ditching cold dark matter entirely. What makes this debate so fascinating is how a tiny tweak to dark matter's properties could rewrite cosmic history. Warm dark matter wouldn't just change the count of dwarf galaxies. It might alter the timeline of star formation, the shape of galactic halos, even the way black holes seeded in the early universe. The Dark Ages weren't just a passive waiting period. They were a canvas where the fundamental nature of matter painted the first strokes of structure. Whether those strokes were bold and sparse or fine and detailed depends on which dark matter story holds true. For now, the evidence remains tantalizingly inconclusive. New telescopes like the Vera Rubin Observatory could tip the scales by mapping millions of faint galaxies, searching for patterns that only warm or cold dark matter can explain. Until then, this theory stands as a reminder that even the darkest corners of the cosmos might hide surprises, and that sometimes the smallest changes in our assumptions can illuminate the biggest mysteries. Billions of ghostly particles may have been streaming through the Dark Ages universe, silently shaping the cosmos with their ethereal touch. These weren't ordinary particles, they were neutrinos born in the unimaginable heat of the Big Bang, flooding space at nearly the speed of light. While today's neutrinos famously pass through entire planets without a single collision, in the early universe they were energetic enough to perform an incredible balancing act, too weak to stop matter from clumping, yet strong enough to subtly steer where those clumps would form. Imagine an invisible cosmic sculptor gently brushing fingers across the universe's wet clay, leaving faint impressions that would harden into galaxies. The cosmic neutrino background is like the cosmic microwave background's shy cousin, an equally ancient relic but far harder to detect. These neutrinos carry snapshots of the universe when it was just 1 second old, long before atoms even formed. As they streamed outward in those early moments, their sheer numbers and energy created a sort of cosmic pressure, smoothing out small density fluctuations while allowing larger structures to grow. Picture blowing across a field of dandelions, the lightest seeds scatter, but sturdier stalks remain. Similarly, neutrinos may have suppressed the formation of tiny proto-galaxies while permitting massive ones to emerge, creating a bottom-up universe where the biggest structures assembled first. Some simulations suggest this neutrino filtering could explain why we don't see as many dwarf galaxies as predicted. They were literally washed away by the neutrino tide. More intriguingly, these particles might have created bizarre neutrino wakes, elongated trails where matter piled up behind moving neutrino concentrations, like cosmic snowdrifts behind a speeding plow. If so, the largest structures in today's universe could bear faint imprints of patterns etched by particles trillions of times smaller than atoms. The challenge lies in proving it. Unlike the CMB's glorious afterglow, the cosmic neutrino background has cooled to near absolute zero. Its particles now so low energy that detecting them may require technology centuries ahead of ours. Yet ingenious methods are being explored, from hunting for subtle distortions in the CMB's polarization to searching for rare neutrino interactions in ultra-sensitive underground detectors. There's even speculation that the James Webb Space Telescope might spot unusual galaxy distributions hinting at neutrinos' ancient influence. What makes this theory profound is its reminder that the universe's largest structures may owe their form to its smallest, most elusive inhabitants. Those first galaxies didn't just grow randomly, they emerged from a cosmic fabric gently tugged and stretched by particles that barely interact with anything at all. The Dark Ages weren't just about absence of light, they were an era where even the most ghostly particles left fingerprints on the cosmos we see today. The universe's first stars weren't just older versions of the sun, they were colossal, volatile beasts that burned bright and died young, forging the very elements that make up our bodies and our world. Scientists call them population 3 stars, and they're one of the greatest unsolved mysteries of the Dark Ages. These stellar pioneers were unlike anything we see today. born from pure hydrogen and helium in a universe that had yet to be polluted by heavier elements. Imagine a star 100 times more massive than our Sun, glowing with a searing blue-white heat so intense it could outshine entire galaxies of modern stars, only to explode in a cataclysmic supernova after mere millions of years. Their brief, brilliant lives were cosmic alchemy in action, transforming simple atoms into the building blocks of planets, life, and eventually us. What makes population 3 stars so extraordinary is their composition, or rather their lack of it. Without metals, what astronomers call elements heavier than hydrogen and helium, these stars couldn't cool efficiently, allowing them to grow to staggering sizes before gravity finally ignited their cores. Some models suggest they may have reached up to 1,000 solar masses, so enormous their surfaces would have rippled with instability, shedding colossal winds of gas into space like celestial hurricanes. Their nuclear furnaces didn't just fuse hydrogen into helium. They forged carbon, oxygen, and even iron in their hearts at breakneck speeds, seeding the cosmos with the raw materials for everything that followed. Yet for all their importance, we've never directly observed one. The reason they lived fast and died young, vanishing before the universe hit its 1 billionth birthday. The closest we've come is spotting distant galaxies with bizarre chemical signatures, hints of ancient supernova so powerful they defy modern stellar physics. These explosions, dubbed pair instability supernova, would have been unlike anything in today's universe, detonating with such force that they left no remnant black hole or neutron star behind, just a spray of heavy elements and a faint echo in the light of their descendants. The legacy of population 3 stars is written in the stars around us. Second-generation stars, known as population 2, contain trace amounts of those first heavy elements, like a family heirloom passed down through generations. Even our Sun, a latecomer population 1 star, carries the chemical fingerprints of those primordial giants. Every atom of gold in your jewelry, every breath of oxygen in your lungs was forged in the hearts of stars that died before Earth even existed. But the mystery goes deeper. Some theories suggest these first stars might not have all died in supernova. A fraction could have collapsed directly into black holes, swallowing their heavy elements before they could enrich the cosmos. Others propose that binary population 3 systems might have spiraled together, creating the first gravitational wave events and seeding supermassive black holes that lurk in galactic centers today. The more we learn, the clearer it becomes the Dark Ages didn't end with a whimper, but with the deafening roar of stars that taught the universe how to build complexity. And here's the twist: finding these stellar ghosts might not be impossible. The James Webb Space Telescope is tuned to hunt for the infrared afterglow of population 3 stars supernova, while future observatories could detect the unique shadows they cast on the cosmic microwave background. If we're lucky, we might catch a glimpse of their dying light, a message in a bottle from an era when the universe was just learning how to shine. Until then, their story remains half-written, a cosmic prologue to everything we know. What if the first lights in the universe weren't stars at all, at least not as we know them? Picture this: colossal spheres of hydrogen and helium, glowing not from nuclear fusion in their cores, but from something far stranger: dark matter annihilating itself in their hearts. These hypothetical monsters, dubbed dark stars, could have been the universe's first luminous objects, burning with a pale, eerie light for millions of years before true stars ever took the stage. Here's how it might have worked. In the early universe, vast clouds of hydrogen would have swirled around clumps of dark matter. Normally, these gas clouds would collapse until fusion ignited, creating conventional stars. But if dark matter particles were dense enough, and if they could annihilate upon contact, releasing energy, something extraordinary would happen. As the gas contracted, dark matter packed into the core would begin annihilating, producing enough heat to counteract gravity's pull. The result, a slow-burning, super-sized object, potentially hundreds of times wider than our solar system, radiating a soft glow powered entirely by invisible particles we still struggle to detect today. The implications are staggering. Dark stars would have behaved unlike any star in the modern cosmos. Instead of blazing at tens of thousands of degrees, their surfaces might have hovered at a relatively lukewarm several thousand, like a dim bulb compared to a spotlight. Yet their sheer size would have made them visible across cosmic distances, their faint light stretched by the expansion of the universe into infrared wavelengths we might just detect with telescopes like JWST. And because dark matter annihilation produces energy so efficiently, these objects could have lasted for millions of years, far longer than fusion-powered stars of similar mass. But the wildest twist isn't their fuel source, it's their fate. When dark matter in the core finally depleted, a dark star wouldn't explode but implode, collapsing into a black hole of unprecedented size. Some theorists suggest this could explain how supermassive black holes appeared so early in the universe's history. They weren't born from stars, but from the remnants of these dark matter engines. It's a cosmic bait and switch. What looks like the first flicker of starlight might actually be the birth cry of a monster. Not everyone's convinced, of course. Critics argue that dark matter's distribution may not have been dense enough to sustain such objects, or that annihilation rates would have been too slow to prevent conventional star formation. Yet recent simulations show that under just the right conditions, dark stars could have formed in the densest regions of the early cosmos. And intriguingly, some of the most distant, puzzling objects JWST has spotted, enormous red blobs with unusual spectra, match predictions for what dark star remnants might look like billions of years later. The beauty of this theory lies in its duality. Dark stars bridge two of cosmology's greatest mysteries, the nature of dark matter and the origins of cosmic structure. If they existed, they weren't just celestial oddities, they were the universe's first experiments in turning darkness into light. And that transformation may have set the stage for everything that followed. The end of the Dark Ages wasn't a gentle sunrise, it was a cosmic wildfire. After hundreds of millions of years of darkness, something tore through the universe's thick veil of hydrogen gas, stripping electrons from atoms in an event so colossal we still debate its cause. Scientists call it reionization, the moment when the fog lifted and light could travel freely across space for the first time. But the culprit behind this great unveiling remains one of cosmology's fiercest debates. Was it the first stars, rogue black holes, or forces we haven't even imagined? Let's start with the starlight scenario. The earliest stars, those blazing population 3 giants, pumped out torrents of ultraviolet radiation, enough to ionize hydrogen atoms in vast bubbles around them. Picture a forest fire spreading from tree to tree, only here, each tree is a galaxy, and the fire is unstoppable ultraviolet flames. Over millions of years, these ionized bubbles overlapped, eventually clearing the cosmic fog entirely. The elegance of this theory lies in its simplicity. Stars ended the starless era, yet there's a problem. Recent observations suggest reionization happened faster and more unevenly than stellar radiation alone can explain. Some regions of the universe became transparent shockingly early, while others lagged behind like a burning piece of paper with random holes. That's where black holes enter the debate. Primordial black holes, or those formed from the first supernova, could have accelerated reionization dramatically. As gas spiraled into these gravitational monsters, it would have heated to millions of degrees, spewing X-rays far more energetic than starlight. These X-rays could penetrate dense clouds of hydrogen that UV light couldn't, ionizing atoms deep inside cosmic nurseries. Even more intriguing, black hole jets might have drilled narrow tunnels through the gas, creating ionized pathways where light could escape. It's a bit like using a blowtorch instead of a match to ignite damp. Would some tools work where others fail? But the plot thickens. Some theorists propose an even wilder idea. dark matter annihilation or decaying exotic particles could have contributed to reionization. If certain types of dark matter particles collided and released energy or spontaneously decayed into radiation, they might have flooded the universe with ionizing particles long before stars dominated. Imagine invisible fireflies flickering in the dark, each flash stripping electrons from hydrogen atoms. While speculative, this could explain why some regions reionized suspiciously early, areas where dark matter happened to cluster more densely. The smoking gun might lie in the subtle patterns of polarized light in the cosmic microwave background. Experiments like the Simons Observatory are hunting for telltale swirls in this ancient glow, imprints that could reveal whether reionization was driven by stars, black holes, or something stranger. Meanwhile, the James Webb Space Telescope peers at galaxies from this epoch, searching for signs of unusually intense radiation that might betray the presence of primordial black holes or exotic particle decay. What's fascinating is how high the stakes are. Reionization didn't just end the Dark Ages, it set the stage for every galaxy, star, and planet that followed. If black holes or dark matter played a major role, it means the universe's rebirth wasn't a solo act, but a collaboration of forces we're only beginning to understand. And that's the ultimate puzzle. To unravel how darkness lifted, we might need to rewrite what we know about the very nature of light. The universe wasn't built with random splatters of matter, it was woven. Imagine a spider's silk stretching across the void, threads of galaxies and gas strung along invisible lines of gravity. This is the cosmic web, the largest structure in existence, and its blueprint was drawn during the Dark Ages in a silent battle between ordinary matter and its mysterious counterpart, dark matter. The story of how this intricate network emerged is one of push and pull, where the universe's fate hinged on a tug of war between forces we're still struggling to understand. Gravity was the loom, but dark matter provided the threads. In the early universe, dark matter, being unaffected by radiation pressure, began collapsing first, forming an invisible skeleton of dense knots connected by wispy filaments. Ordinary hydrogen gas, though slower to respond, eventually followed these pathways, flowing into the gravitational wells like water finding the cracks in a sidewalk. Over hundreds of millions of years, this process sculpted vast, intersecting rivers of matter, with galaxies forming at the intersections like glittering beads on a necklace. The cosmic web wasn't just a structure, it was a highway system for the universe's growth, directing the flow of material toward its destiny. What's astonishing is how delicate this balance was. Too much dark matter and gas would have collapsed into chaotic clumps instead of elegant filaments. Too little, and the universe might have remained a formless haze. Computer simulations reveal the cosmic web's structure with eerie precision, matching the distribution of galaxies we observe today. These virtual universes show dark matter as an unseen puppeteer, its strings guiding ordinary matter into place long before starlight could illuminate the stage. Yet the web wasn't uniform. Tiny quantum fluctuations from the Big Bang, those same ripples preserved in the cosmic microwave background, meant some filaments grew thicker, some intersections denser. This cosmic lottery determined where galaxy clusters would thrive and where vast voids would stretch, empty and dark. It's as if the universe rolled a trillion-sided die during the Dark Ages, and the results shaped everything we see. The most captivating part, we can still glimpse this ancient web today. When astronomers map thousands of galaxies, their positions trace the same filaments and voids first seeded in the Dark Ages. Even more remarkably, the leftover gas between galaxies, the so-called intergalactic medium, still carries the imprint of this structure, like invisible ink revealing a hidden message. By studying how light from distant quasars filters through these filaments, scientists have found evidence of the web's primordial hydrogen nearly unchanged for billions of years. But the cosmic web isn't just a relic, it's alive. Even now, galaxies slide along its filaments, drawn toward massive clusters in a slow-motion dance that will continue for eons. The Dark Ages didn't just set the stage, they spun the threads that would bind the universe together. And as we unravel their secrets, we're not just studying the past, we're reading the map of our cosmic future. Among the most mind-bending theories about the Dark Ages is the possibility that gravity itself wasn't constant, that an invisible, shape-shifting force subtly altered its strength across the cosmos, leaving fingerprints in the very fabric of galaxy formation. This is the essence of the chameleon field theory, where hypothetical scalar fields entities that permeate all of space may have meddled with gravity's pull during the universe's most mysterious era. Picture gravity as a radio dial, its volume turned up in some regions of space and muted in others, all by the influence of a field that adapts to its environment like a cosmic chameleon. The math behind this idea is as elegant as it is radical. Unlike the steady gravitational force we experience today, chameleon fields would have varied their effect based on local conditions. In dense regions like galaxy clusters, the field would suppress itself, minimizing its impact on gravity. But in the vast, empty voids between galaxies where matter is sparse, the field could emerge fully, weakening gravity's grip over intergalactic distances. This behavior isn't just theoretical whimsy. It could solve a glaring inconsistency in modern cosmology: why galaxies rotate faster than predicted by standard gravity models, and why the universe's expansion accelerates. If chameleon fields were active during the Dark Ages, they might have subtly warped the growth of cosmic structure in ways that still echo today. What's fascinating is how this theory turns our understanding of the Dark Ages upside down. Instead of a passive era where matter slowly clumped under gravity's unchanging rule, the chameleon field paints a picture of dynamic manipulation where the very rules of attraction shifted from place to place. Dense proto-galactic clouds might have collapsed faster in certain regions, explaining why some galaxies appear improbably mature for their age. Meanwhile, voids could have stretched even emptier as weakened gravity allowed matter to disperse more freely. The cosmic web we see today, with its intricate filaments and cavernous voids, might bear the scars of this invisible hand at work. Evidence for this idea is tantalizing but elusive. Some astronomers point to peculiar patterns in galaxy distributions, unusually even spacing between clusters, or filaments that appear more stretched than simulations predict, as possible signatures of chameleon field's influence. Others study the bending of light around massive objects, searching for anomalies that might betray gravity's historical fickleness. Even the cosmic microwave background could hold clues. Subtle asymmetries in its polarization might record where and how gravity's strength fluctuated during the Dark Ages. Yet not all researchers are convinced. Critics argue that chameleon fields, while mathematically elegant, may be a solution in search of a problem. That adjustments to dark energy or modified theories of gravity could explain the same observations without invoking undiscovered fields. There's also the challenge of detecting something designed to hide. By definition, a chameleon field would be strongest where matter is rarest, making it fiendishly difficult to observe directly. The stakes, however, are enormous. If chameleon fields exist, they wouldn't just rewrite the story of the Dark Ages, they'd redefine our understanding of fundamental forces. Gravity, the universe's architect, might not be the steadfast constant we assumed, but a variable player in a much stranger cosmic drama. And if we're right about their role, the shadows of those ancient fluctuations might still linger, etched into the galaxies and voids we see today. A ghostly reminder that even the laws of physics may have once been more fluid than we dare imagine. We think of the Dark Ages as ancient history, but what if they also hold clues to the universe's final fate? Among the wildest possibilities is a connection between those primordial shadows and the cosmos' eventual destruction in a big rip, a catastrophic endgame where phantom energy tears reality apart atom by atom. Here's the eerie part. Subtle signs of that future apocalypse might have been imprinted during the Dark Ages, hidden in how the first structures formed in the darkness. Phantom energy isn't your typical dark energy. While ordinary dark energy accelerates the universe's expansion at a steady pace, phantom energy grows stronger over time, its repulsive force eventually overwhelming gravity, then electromagnetism, then even the nuclear forces holding atoms together. Picture a cosmic crescendo where space itself stretches faster than light can travel, shredding galaxies, stars, and finally the fabric of spacetime. Most theories place this event trillions of years in the future, but its roots could stretch back to the universe's first chapters. During the Dark Ages, phantom energy, if it existed, would have been unimaginably weak, a whisper against gravity's roar. Yet even a faint trace could have altered how matter clumped together in critical ways. Simulations show that phantom energy's unique signature would suppress the growth of small-scale structures like dwarf galaxies, while paradoxically accelerating the formation of massive clusters. This isn't just theoretical. Some observations of the early universe reveal puzzling voids and galaxy distributions that align suspiciously with phantom energy models. It's as if the cosmos was already practicing for its own dissolution. The smoking gun might lie in reionization. If phantom energy subtly warped the timeline of starlight piercing the cosmic fog, we might detect anomalies in how quickly different regions of space became transparent. Telescopes like JWST are now hunting for these irregularities, mapping the epoch's uneven patches like detectives studying cracks in a breaking dam. Even more tantalizing are hints from quasars' ancient beacons whose light filtered through the Dark Ages hydrogen clouds. Specific distortions in their spectra could betray phantom energy's early stirrings, but the real mind-bender is this. If phantom energy's fingerprints are indeed hidden in the Dark Ages, it suggests the universe's birth and death are intertwined in ways we've barely begun to grasp. The same quantum fluctuations that seeded galaxies might have also planted the seeds of cosmic doom, a duality where creation and destruction emerge from the same primordial code. Critics counter that phantom energy remains speculative, and that alternative explanations like variations in dark matter or exotic particle interactions could account for any anomalies. Yet the possibility lingers. The Dark Ages weren't just a prelude to light, but the first whisper of an ending so absolute, it makes black holes look gentle. And if that's true, then studying this ancient era isn't just about uncovering our past, it's about reading a cosmic will, written in the faintest ink of hydrogen and shadow. What if the Dark Ages weren't just a chapter in our universe's story, but a whisper from countless others? The multiverse theory, the idea that our cosmos is just one bubble in an infinite froth of parallel realities, might seem like pure speculation. But some cosmologists believe that if these other universes exist, they could have left faint scars on our own during its darkest era, anomalies hidden in the cosmic microwave background or the large-scale structure of space itself. Think of it like standing in a hall of mirrors where reflections aren't perfect. If another universe brushed against ours during the Dark Ages, even briefly, the gravitational distortion from that collision might have warped how matter clumped together in our early cosmos. These cosmic bruises could linger as odd patterns in the distribution of galaxies, strange voids or filaments that curve in ways gravity alone can't explain. Some researchers have already spotted puzzling asymmetries in the cosmic microwave background that defy standard models, cold spots and uneven patches that just might be signatures of a multiversal encounter. Then there's the radiation angle. In a hypothetical multiverse, each universe could have different fundamental constants, stronger gravity, weaker electromagnetism, even extra dimensions. If a neighboring universe with slightly different physics nudged ours, the imprint might linger in the way primordial light polarized during the Dark Ages. It's like finding a fingerprint on a frozen lake, except the finger belongs to a reality with entirely different rules. the most tantalizing clues could come from quantum entanglement. In some multiverse models, particles in separate universes remain subtly linked, creating correlations that defy local physics. If such connections existed during the Dark Ages, they might have left statistical fingerprints in the way hydrogen clouds distributed themselves, patterns that look random unless you know to search for a hidden hand. Skeptics argue these anomalies could have mundane explanations: instrumental noise, statistical flukes, or gaps in our understanding of conventional cosmology. But if even one of these oddities holds up under scrutiny, it could be the first hard evidence that our universe isn't alone. The Dark Ages weren't just a time of darkness, they might have been a crossroads where the shadows of other realities briefly flickered into view. What if the Dark Ages left behind a cosmic cipher, one that suggests the entire universe is actually a hologram? This isn't science fiction. It's a radical idea from string theory called the holographic principle, which proposes that all the information in our three-dimensional reality might actually be encoded on a two-dimensional surface at its boundary, like a projector casting a three-dimensional movie from a flat screen. And if this is true, the Dark Ages could hold the first fingerprints of this mind-bending reality. The holographic principle stems from an unsettling discovery about black holes. Their entropy, or information content, scales with their surface area, not their volume. This implies that the universe itself might operate the same way, with every event inside it, every star, every atom, even your thoughts being mere projections of data stored on some distant, invisible horizon. During the Dark Ages, when the universe was simpler and quantum fluctuations were imprinting their patterns on the cosmos, these holographic pixels might have left subtle distortions in the fabric of space-time, like glitches in a celestial simulation. Here's where it gets wild. Those primordial quantum fluctuations we see in the cosmic microwave background, the ones that seeded galaxies, might not be entirely random. If the holographic principle is correct, they could carry hidden correlations, patterns that only make sense if space-time is fundamentally two-dimensional. Imagine shaking a sheet of paper and seeing the wrinkles form in 3 dimensions, except the paper is the edge of reality itself, and the wrinkles are galaxies. Some theorists argue that certain anomalies in the CMB, like unexpected alignments of temperature fluctuations, could be echoes of this holographic code written in the universe's infancy. But how would this work in practice? During the Dark Ages, the universe was small enough that quantum gravitational effects, usually negligible today, might have been significant. If space-time was indeed emerging from a deeper, two-dimensional reality, its fluctuations could have exhibited telltale signatures, statistical asymmetries, unusual non-local connections between distant regions, or even forbidden patterns in the polarization of ancient light. It's like finding a signature on the cosmic microwave background that reads, "Made in a lower dimension." Skeptics point out that these anomalies could have mundane explanations: instrumental noise, incomplete data, or our imperfect understanding of cosmic inflation. Yet the tantalizing possibility remains. If the holographic principle shaped the Dark Ages, it didn't just influence the universe's structure, it might have dictated the rules of existence itself. Every galaxy, every star, every atom could be part of a grand illusion, projected from a reality we've yet to perceive. And if we're right, the greatest mystery of the Dark Ages isn't what happened, it's where it was all really happening. We think of the early universe as a place where galaxies were the main characters, bright beacons emerging from the darkness. But what if we've had it backward all along? The void dominance theory flips the script, suggesting that the real architects of the Dark Ages weren't the glowing islands of matter, but the vast, empty voids between them. These cosmic deserts, spanning hundreds of millions of light years, might have been pulling the strings all along, steering the expansion and structure of the young cosmos in ways we're only beginning to understand. During the Dark Ages, gravity was the universe's sculptor, but voids played a deceptive game. While matter clumped into filaments and proto-galaxies, these empty regions exerted their own influence, pushing outward as space itself stretched. Picture a balloon inflating unevenly, with some areas expanding faster than others. The voids weren't just passive gaps, they were cosmic vacuum cleaners, growing larger as they siphoned gas and dark matter away from their edges. Over time, this created a feedback loop. The bigger a void grew, the more aggressively it pulled surrounding material into its emptiness, accelerating its own expansion. Here's where it gets counterintuitive. While we often focus on how galaxies formed, the voids might have dictated the pace. Some models suggest these regions weren't just byproducts of structure formation. They were the driving force behind reionization, the universe's great awakening. How, as voids expanded, they squeezed gas into tighter filaments and knots, heating it until it sparked star formation along their borders. The very emptiness of voids could have acted like a cosmic pressure cooker, triggering the birth of galaxies at their edges while keeping their interiors dark for eons longer. The evidence hides in modern sky surveys. When astronomers map the universe's large-scale structure, they find something peculiar. Galaxies aren't randomly scattered, they cling to the surfaces of vast, bubble-like voids, as if painted onto the walls of an invisible labyrinth. Even more telling, these voids aren't perfectly empty. Some contain faint, isolated galaxies or wisps of gas that move too fast for standard gravity to explain. This hints that voids might harbor their own peculiar gravitational fields, shaped by dark energy or exotic physics we've yet to uncover. But the real twist is how this theory reframes the Dark Ages legacy. If voids dominated, then the universe's expansion wasn't a uniform march, it was a tug of war between emptiness and structure. Regions with dense dark matter halos resisted expansion, while voids ballooned unchecked, creating a cosmic patchwork where time itself might have flowed differently. Light traveling through these emptinesses would have stretched further, redshifted more severely, making the voids appear even larger than they were, a hall of mirrors on a universal scale. The implications ripple outward. If voids were the puppeteers, then the first galaxies weren't pioneers, they were bystanders shaped by the negative space around them. Even today, the largest voids continue to grow, their expansion fueled by dark energy's push. In a way, the Dark Ages never truly ended. They just retreated into these ever-widening gaps, their ghostly influence still echoing in the hollows of the cosmos. And that raises a haunting question. Are we living in the aftermath of void's reign, or is their dominance still unfolding, invisible to all but the most patient observers? What if the Dark Ages harbored structures that defied not just space but time itself? Enter the time crystal, a bizarre phase of matter that pulses in a repeating cycle without energy input, like a perpetual motion machine at the quantum scale. Unlike ordinary crystals with atoms arranged in predictable spatial patterns, time crystals have atomic structures that oscillate indefinitely in time, their components flipping states with clockwork regularity, even in the universe's lowest energy state. It sounds like science fiction, but labs have created fleeting versions of these objects using supercooled ions and lasers. Now, some theorists propose an electrifying possibility. The extreme conditions of the early universe might have forged primordial time crystals spontaneously, weaving rhythmic patterns into the fabric of the Dark Ages. The idea hinges on a cosmic sweet spot. During the universe's infancy, temperatures and energy densities were so extreme that matter could exist in phases utterly alien to today's cosmos. Quantum fields, still settling after the Big Bang's tumult, might have briefly stabilized into time crystalline arrangements, self-sustaining loops of particles flipping between states like a celestial metronome. Picture a region of space where hydrogen atoms didn't just drift randomly but pulsed in unison, their electrons synchronizing across light years without any external trigger. These structures wouldn't have been permanent. As the universe expanded and cooled, they'd dissolve like snowflakes in warm wind. but for a fleeting moment, time itself could have had a crystalline structure. Here's where it gets stranger. If time crystals existed, they might have left fingerprints on the Dark Ages' two most famous relics, the cosmic microwave background and the 21-centimeter hydrogen signal. Their rhythmic oscillations could have imprinted subtle, repeating patterns in the polarization of ancient light, like finding a stutter in the universe's first whisper. Even more intriguingly, time crystals' synchronized pulses might have briefly amplified certain wavelengths of the hydrogen signal, creating anomalous echoes in the radiostatic we now hunt for. It's the cosmological equivalent of detecting a ghostly drumbeat in a silent room. Critics argue that without a clear mechanism to stabilize such structures at cosmic scales, time crystals remain speculative. Yet proponents point to emerging lab experiments where time crystalline behavior appears in unexpected systems, from superconducting qubits to neutron star crusts. If quantum mechanics allows these phenomena in a lab dish, why not in a universe a million times hotter and denser? The implications ripple beyond curiosity. If time crystals flickered in the Dark Ages, they might have subtly guided how matter clumped together. Regions where these temporal patterns formed could have developed unusual density waves, seeding galaxies in spirals rather than random clusters. Or perhaps their breakdown released bursts of coherent energy, jump-starting star formation in pockets of the cosmos. The universe's first structures might not have been sculpted by gravity alone, but by the ghostly ticking of clocks woven into space-time itself. And that raises a profound question. Could traces of these temporal architectures linger today? Some models suggest that if time crystals were entangled with dark matter, their echoes might still resonate in the odd rotations of distant galaxies or the timing of pulsar flashes. The Dark Ages weren't just a prelude to light, they might have been a hall of mirrors where time itself learned to dance. And if we listen closely to the cosmos' oldest signals, we might just catch the rhythm. Neutrinos are the universe's most elusive escape artists. Billions of them slipped through the infant cosmos like ghosts through walls, carrying away precious energy that might have jump-started the first stars. This great neutrino exodus happened just 1 second after the Big Bang, when the universe was still a seething plasma 10 billion times hotter than the Sun. At that critical moment, these featherweight particles stopped interacting with matter entirely, streaming outward at nearly light speed and taking a staggering amount of heat with them. It's as if someone pulled the plug on the cosmic bathtub, draining warmth that could have fueled star formation for eons. Here's why this matters for the Dark Ages. Energy isn't just about temperature, it's the currency of structure formation. The more energy trapped in a gas cloud, the harder it is for gravity to compress that cloud into stars. By whisking away thermal energy, neutrinos essentially robbed the early universe of its ability to create dense pockets quickly. Picture trying to freeze a lake while invisible currents constantly stir the water. The ice would form slower and unevenly. Similarly, the first star-forming regions had to fight against this energy deficit, delaying their collapse by millions of years, but the plot thickens. Recent simulations suggest neutrinos didn't just cool the universe uniformly, they created patchwork conditions where star formation happened in fits and starts. Regions where neutrinos clustered slightly denser would have lost more energy, becoming colder and collapsing earlier. Meanwhile, zones with fewer neutrinos retained heat, staying puffed up like cosmic soufflés. This could explain why some galaxies in the JWST deep field images appear surprisingly mature while their neighbors seem underdeveloped, an unexpected diversity forged by neutrino shadows. The most tantalizing clue lies in the cosmic neutrino background, the faint afterglow of this particle exodus. While we can't detect it directly yet, its imprint might hide in subtle distortions in the cosmic microwave background's polarization patterns, swirls, and eddies that record how neutrinos tugged at spacetime as they fled. Future observatories like CMB S4 aim to read these whispers, potentially confirming whether these ghostly particles truly throttled the universe's dawn. Yet there's a beautiful irony here. The same neutrinos that may have prolonged the dark ages also guaranteed their end. By smoothing out the universe's energy distribution, they prevented runaway collapses that could have birthed monstrous, short-lived stars. Instead, they enabled a steadier, more sustainable path to starlight, one that allowed galaxies like ours to eventually emerge. The universe's longest night wasn't a flaw in the design, but a necessary pause orchestrated in part by particles so light they barely seemed to exist at all. We know the four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces rule the cosmos today. But the Dark Ages might have played host to a fifth, a shadowy player that flickered into existence just long enough to tweak the universe's blueprint before vanishing without a trace. This isn't wild speculation, it's a serious response to some of cosmology's nagging puzzles. Why do certain primordial galaxies appear too massive for their age? Why does the cosmic web's structure show odd symmetries that gravity alone can't explain? The answer might lie in a force that thrived only when the universe was dark, a temporary architect that shaped matter's first strokes before handing the reins to the familiar four. Picture this: in the seething chaos just after the Big Bang, particles didn't just interact through the forces we know. They might have been tugged by an additional carrier, a hypothetical particle with just enough strength to nudge atoms during the Dark Ages before fading into irrelevance. Some models suggest this fifth force could have been tied to dark matter, acting as a dark electromagnetism that helped clump invisible particles into halos faster than gravity could manage alone. Unlike gravity's patient pull, this force might have operated over specific, limited ranges, creating dense knots of matter precisely where the first galaxies would later ignite. Think of it as cosmic Velcro, selectively sticking dark matter together in patterns that gravity would have taken eons to arrange. The most tantalizing evidence comes from the cosmic microwave background. Those faint temperature fluctuations, the ones that seeded all structure, some exhibit strange alignments, so-called anomalous correlations, where hot and cold spots seem to coordinate in ways that defy standard physics. It's as if an invisible hand briefly reached into the early universe and tweaked the dice rolls. A fifth force, active only during the Dark Ages, could explain these irregularities. If this force mediated interactions between dark and ordinary matter, even fleetingly, it might have left ghostly fingerprints in the way hydrogen gas pooled or how the first black holes formed. Critics argue that inventing new forces is a slippery slope, a fix for every gap in our knowledge, yet the math is compelling. Certain string theory variants predict extra forces that decay as the universe expands, leaving relics in the form of ultra-light particles. Others propose that the fifth force wasn't a force at all, but a side effect of space-time itself crystallizing into its current form, like ice settling into a rigid structure as it cools. Either way, the Dark Ages would have been the era when these phenomena peaked, imprinting their influence on the cosmos before retreating into obscurity. The kicker: we might be able to test this. If a fifth force altered how dark matter clumped, its echoes could linger in today's galaxy rotations, where stars orbit faster at the edges than gravity alone predicts. Future telescopes mapping the distribution of ancient hydrogen might also spot unnatural ripples patterns betraying an extra push or pull in the universe's youth. The Dark Ages weren't just a blank slate. They could have been a laboratory for physics we'll never see again, a fleeting chapter where the rules were written in invisible ink. And if we're right, peeling back those layers might finally reveal why the cosmos looks the way it does, not by accident, but because something extra was pulling the strings. Einstein's theory of relativity and quantum mechanics are the twin pillars of modern physics, yet they refuse to speak the same language. One rules the cosmos with graceful curves of space-time, while the other governs the subatomic realm with chaotic probabilities. For decades, scientists have searched for a bridge between these worlds, a theory of quantum gravity that could unite them. But what if the answers aren't hidden in particle colliders or black hole equations? What if they've been lurking all along in the silent depths of the Dark Ages? This theory hinges on a radical idea that the universe's murky transition from darkness to light might have frozen quantum gravity's fingerprints into the cosmos itself. During the Dark Ages, space-time was far smaller and denser than today, a realm where quantum effects could have warped gravity's fabric on scales we'd never see in our stretched-out modern universe. Picture a frozen pond in winter. The cracks in the ice aren't random. They record every stress and strain the water endured as it froze. Similarly, the patterns of galaxies and voids we see today might be cosmic cracks, preserving how quantum gravity tugged at spacetime when the universe was young. The smoking gun could lie in the cosmic microwave background's tiniest fluctuations. If quantum gravity altered how spacetime rippled during inflation, the universe's explosive first moments, those distortions might have propagated through the Dark Ages, subtly warping how matter clumped together. Some models predict these imprints would appear as strange, non-random twists in the CMB's polarization patterns, like invisible hands twisting the universe's first light. Others suggest that primordial black holes, spacetime's quantum knots, could have formed during this era, their birth cries echoing in gravitational waves we might yet detect. But the boldest clue might be hiding in plain sight, the universe's unexpected smoothness. Quantum mechanics loves randomness, yet the cosmos is suspiciously uniform on large scales. This paradox could resolve if quantum gravity acted as a cosmic referee during the Dark Ages, enforcing rules we don't yet understand. Imagine rolling a pair of quantum dice. They could land on any number, yet somehow they always average out to 7. That eerie fine-tuning might reflect quantum gravity's hidden hand, ensuring the universe didn't tear itself apart before starlight could emerge. The hunt for these clues is pushing technology to its limits. Future gravitational wave detectors could listen for whispers from the Dark Ages, frequencies so low they'd reveal spacetime's quantum vibrations. Meanwhile, next-generation telescopes are scanning the CMB for anomalies, subtle swirls, or forbidden symmetries that defy conventional physics. Even the James Webb Space Telescope's deep-field images might hold hints, as quantum gravity could have skewed the shapes and distributions of the earliest galaxies in ways we're only beginning to model. Skeptics argue that without a definitive quantum gravity theory, these searches are like navigating without a map. Yet the Dark Ages offer something unique, a snapshot of the universe when quantum and gravitational forces were perfectly balanced, neither drowned out by radiation nor diluted by expansion. It was the Goldilocks epoch for quantum gravity, not too hot, not too cold, but just right for its effects to leave permanent marks, and that raises a thrilling possibility. The universe's greatest unsolved puzzle might not require futuristic experiments or alien technology to crack. The answers could be etched in the darkness all around us, written in a language of ancient light and invisible ripples. The Dark Ages weren't just a gap in cosmic history, they might be the Rosetta Stone we need to finally read the full story of reality. What if the Dark Ages weren't the beginning of the universe's story, but merely the latest chapter in an endless cycle of cosmic death and rebirth? This is the essence of the oscillating universe theory, a radical vision where the Big Bang wasn't a singular event, but one in an infinite series of expansions and contractions. In this model, the eerie quiet of the Dark Ages might not have been an empty void at all, but a cosmic graveyard, a silent testament to a previous universe that had collapsed under its own gravity before ours was born from its ashes. Imagine the remnants of an earlier universe lingering in the depths of that primordial darkness. As that doomed cosmos crunched inward during its Big Crunch, unimaginable pressures might have scrambled fundamental constants and particles, leaving behind ghostly anomalies in the fabric of spacetime. When our universe burst forth from that collapse, traces of the old order, subtle warps in gravity, patches of unusual dark matter distribution, or even rogue black holes that survived the transition, could have seeped into our dark ages like echoes in a cave. These scars wouldn't just be relics, they'd be active players in how our cosmos evolved, nudging the first structures to form in peculiar ways. The most tantalizing evidence might lie in the cosmic microwave background's anomalies, those infamous cold spots and unexpected asymmetries that defy standard cosmology. Could these be bruises from a pre-Big Bang collision, or imprints of structures from a prior universe that somehow persisted through the collapse? Some cyclic models suggest that gravitational waves from the death throes of the previous cosmos might have reverberated into ours, leaving faint spiral patterns in the CMB's polarization, like fingerprints on a window between realities. But the wildest implication isn't just about the past, it's about the future. If the universe oscillates, then our own dark ages might one day return in reverse. As dark energy accelerates expansion, galaxies will fade from view, stars will burn out, and space itself may stretch into an endless, lightless void, a mirror of the primordial darkness. Yet in this model, that emptiness won't be the end. Eventually, dark energy could decay, gravity would regain dominance, and the universe would collapse anew, seeding another Big Bang and another cycle of cosmic dawn. The Dark Ages wouldn't be a one-time event, but a recurring intermission in an infinite cosmic drama. Critics argue that without a mechanism to reset entropy, the universe's inevitable slide into disorder, each cycle would grow progressively more chaotic, making the pristine order we observe today statistically impossible. Yet some theorists propose that the Big Crunch itself might renew entropy, scrubbing the cosmic slate clean through processes we've yet to understand. Others suggest that our universe could be a bubble in a multiverse, with each cycle birthing not an identical twin, but a twisted sibling with slightly altered physics. Whether poetic speculation or profound truth, the oscillating universe theory forces us to confront a humbling possibility. The Dark Ages might not have been our universe's first night. They could be a recurring silence, a pause between cosmic breaths where remnants of past realities whisper to future ones across the abyss of time. And if that's true, then every galaxy, every star, and every atom carries within it the faintest memory of universes long gone, waiting to awaken again. What if the Dark Ages weren't just mysterious but flawed? Imagine a cosmic glitch in the universe's code, a subtle error in the simulation's rendering of those lightless eons. The simulated universe theory, once relegated to philosophy circles, has gained eerie traction in modern physics, with some researchers proposing that anomalies in the Dark Ages structure could be the pixelated seams in our supposedly perfect reality. At the heart of this idea is a simple but unsettling question. Why do certain aspects of the Dark Ages defy our most elegant models? Tiny discrepancies in the cosmic microwave background, random cold spots, improbable alignments of temperature fluctuations could be more than statistical noise. They might resemble the artifacts you'd find in a virtual world where the resolution isn't quite fine enough to hide the underlying code. Picture a video game where distant textures blur or repeat unnaturally, now scale that up to the universe itself. One particularly puzzling anomaly is the axis of evil, a controversial pattern in the CMB where temperature fluctuations appear oddly aligned across billions of light years, as if the universe had a preferential direction baked into its programming. Standard cosmology insists the cosmos should be isotropic, the same in all directions. Yet here we are, staring at what looks suspiciously like a coordinate system's leftover grid lines. Even stranger, simulations of the Dark Ages produce hydrogen distribution patterns that are almost too uniform, like a procedural generation algorithm stuck on repeat, subtly betraying its artificial origins. Then there's the matter of energy conservation, or lack thereof. Quantum fluctuations during the Dark Ages should have balanced out perfectly, yet some models suggest pockets of spacetime where energy appears to flicker inexplicably, as if the simulation's physics engine cut corners to save processing power. It's the cosmic equivalent of a lagging video call, where the screen freezes just long enough to make you question what's really happening behind the scenes. But the most provocative evidence might come from black holes. These gravitational abysses are often called the universe's garbage collectors, but what if they're actually memory buffers? In some simulated universe models, information swallowed by black holes isn't destroyed but compressed and stored, much like a computer offloading data to free up RAM. The Dark Ages' lack of observable black holes could imply they were still in debugging mode, their event horizons glitching as the simulation's protocols were still being refined. Skeptics, of course, have counterarguments. They point out that anomalies could simply reflect gaps in our knowledge, like dark matter's quirks or inflation's untested variants. But the simulation hypothesis gains traction because it doesn't just explain glitches, it predicts them. If our universe is a construct, its earliest epochs would be the most likely to show cracks where the simulation's initial conditions weren't perfectly smoothed over. The implications are staggering. If the Dark Ages contain deliberate Easter eggs, patterns, or mathematical constants repeating where they shouldn't, it could hint at a programmer's signature. Some scientists have even proposed scanning the CMB for computational checksums, hidden validations that the universe is running as intended. Yet here's the twist: even if we are in a simulation, the Dark Ages mysteries don't become less profound. They become more so, because if this is all code, then the glitches aren't bugs, they're clues to the rules of a reality far grander than our own. And that means the silence of the cosmic night might not be emptiness at all, but the hum of a machine we're only beginning to hear. The universe, it seems, has a knack for dramatic transformations, but even the most spectacular changes require careful preparation. Think of the Dark Ages not as an empty void, but as the universe taking a deep breath before its next great act. In the chaos following the Big Bang, matter was still too hot, too disorganized to build anything lasting. The cosmos needed time not just to cool, but to sort itself out, to lay the invisible groundwork for everything that would follow. This theory suggests the Dark Ages weren't a delay, but a cosmic reset, a necessary intermission where the universe recalibrated its own rules before stepping into the light. Consider how nature operates on Earth. A forest fire might seem destructive, but it clears the way for new growth, recycling nutrients into the soil. The Dark Ages could have served a similar purpose, not by destroying, but by pausing. During this quiet stretch, quantum fluctuations from the Big Bang had time to amplify. Gravity could steadily pull matter into denser configurations, and even dark matter's invisible scaffolding could solidify. Without this pause, the universe might have rushed into star formation too quickly, producing a mess of unstable, short-lived stars that burned out before galaxies could properly assemble. Instead, the Dark Ages allowed the cosmos to buffer, like a computer loading a complex program in the background before displaying it smoothly. The evidence lies in the universe's startling precision. The density variations imprinted in the cosmic microwave background were minuscule, just 1 part in 100,000, yet they were enough. Over hundreds of millions of years, these tiny seeds grew into galaxies, clusters, and the vast cosmic web. Had the Dark Ages been shorter, those fluctuations might not have had time to mature. Too long, and matter could have scattered too thinly, preventing structure altogether. It's as if the universe struck a perfect balance between patience and action, waiting just long enough for gravity to work its magic without losing momentum. This idea reframes the Dark Ages as a kind of cosmic incubation period. Life on Earth requires specific conditions to emerge, not just water and energy, but time for chemistry to become biology. Similarly, the universe needed more than raw materials to build galaxies. It needed the right rhythm. The delay allowed hydrogen gas to reach optimal temperatures for cooling and collapse, enabled dark matter halos to grow large enough to anchor future galaxies, and even let mysterious forces like dark energy or primordial magnetic fields settle into their roles. Perhaps most compelling is the role of entropy, the universe's tendency toward disorder. After the Big Bang's furious expansion, the Dark Ages may have been a phase where entropy's growth slowed, creating pockets of localized order. Like a sculptor letting clay stiffen before carving finer details, the universe used this era to stabilize, ensuring that when stars finally ignited, they did so in an environment ready to nurture planets, molecules, and eventually, the curious minds that would one day ponder it all. The beauty of this theory isn't just in its elegance, but in its humility. It suggests that even the cosmos understands the value of waiting, that darkness isn't emptiness but preparation. Every galaxy, every star, every atom in our bodies exists because the universe had the patience to reset, recalibrate, and rebuild. The Dark Ages weren't an absence of light. They were the universe's way of ensuring that when the light finally came, it would last. From primordial black holes weaving gravity's invisible web to phantom forces tweaking the cosmos expansion, each of these 30 theories paints the Dark Ages not as an empty void, but as a cosmic stage where reality itself was being rewritten. Some suggest dark stars flickered in the abyss, their strange glow fueled by annihilating particles we've yet to detect. Others propose quantum ripples stretched across spacetime, freezing into galactic blueprints while time crystals pulsed in the shadows. Could magnetic fields whispered into existence during inflation have shaped the first stellar nurseries? Or did neutrinos streaming through the infant universe like ghostly winds carry away just enough heat to delay the dawn? Then there's the spine-chilling possibility that we're seeing echoes of a prior cosmos in the CMB's anomalies, bruises from a multiversal collision, or artifacts from a simulated reboot. Maybe the Dark Ages were less about absence and more about reset, a cosmic breathing room where entropy paused just long enough for complexity to emerge. Whether it's actions cooling the primordial soup, voids sculpting the cosmic web, or a fifth force nudging dark matter into place, every theory offers more than answers, it reframes the questions. So here's the ultimate puzzle, with clues scattered across ancient light, gravitational waves, and the very structure of galaxies. Which thread will lead us out of the labyrinth? Could the key lie in the 21-centimeter static we're straining to hear, or in the quantum gravity signatures hiding in plain sight? The Dark Ages didn't just shape the universe, they're daring us to rethink physics itself. Now over to you, which theory grips your imagination? A cosmos woven by time crystals, a hologram projected from the void, or something wilder still? Hit subscribe and join us as we chase the next cosmic enigma, because the universe's greatest stories are written in the gaps between what we know and what we've yet to discover.